Good afternoon and welcome to the Sachs lecture. Let me begin by telling you a little bit about the Sachs lecture. First, to introduce myself, I'm Tom James, Provost and Dean of the College at Teachers College. How's that? Is that better? The Sachs lecture has been around Teachers College since 1930. So there aren't that many current courses or programs or really anything except the buildings about which we can say that this has been an active, yearly, ongoing activity at Teachers College. It was endowed in order to provide a lecture or set of lectures that would give us new information about education as it's being practiced and studied in the United States. And that is certainly what we have today, and that's been very much the tradition here. Our Sachs lecturer this year is Ryan Baker, and I'm going to tell you a little bit about him before he begins his presentation. Ryan Baker is our Sachs lecturer, but also this year a visiting associate professor at Teachers College. He earned his Ph.D. in human-computer interaction from Carnegie Mellon University. And he was a post-doctoral fellow in the learning sciences at the University of Nottingham. He did his undergraduate work at Brown University, where he majored in computer science. He has been an assistant professor of psychology and learning sciences at Worcester Polytechnic Institute, and he previously served as the first technical director of the Pittsburgh Science of Learning Center's DataShop, which is the largest public repository for data on the interaction between learners and educational software. Notably, and quite relevant to our event today, Ryan Baker is currently the founding president of the International Educational Data Mining Society. He's also associate editor of the Journal of Educational Data Mining. His own research combines educational data mining, learning analytics, and quantitative field observation methods. His aim is to understand how students respond to educational software and what impact those responses have on their learning. He studies these issues with intelligent tutors, with simulations, and through educational games. In recent years, Ryan and his colleagues have explored ways of making inferences in real time about student motivation, meta-cognition, affect, and robust learning. Now I'm going to introduce Ryan Baker, who's going to tell you more about what all those categories mean. Thank you very much.
Thank you very much for the introduction, Provost James, and thank you, President Furman, for having me, and thanks to all of you for welcoming me here to Columbia Teachers College. It's a great honor to be here. So today I'm going to talk about educational data mining, predict the future, change the future. So we live in a world of big data, and every day almost every one of us generates lots of data with almost everything we do. Take, for example, cookies. Internet browser cookies in specific. My internet browser cookies know everything about me. There I am. They know I'm fluent in English and Portuguese. They know that I'm married with children. There's my son there who's really taken after me. They know I'm a college professor. They know that I read Kindle documents, but I do so on an iPad. They know that I travel internationally for work. They know that I stay in cheap hotels when I travel internationally for work. They know I like operas by Philip Glass. And they also know that I love to watch videos of Barney the dinosaur online. My gosh, I just can't get enough of those. And all this information is used for the noble purpose of selling me more stuff. When we have huge amounts of data like that, we can use automated analyses called data mining to find out useful things. even for purposes beyond selling more stuff. Big data and methods for working with big data have played an important role in science for quite a while, in fields like physics, biology, and climate science. In climate science, methods for dealing with big data have led to better climate models that give us at least a few days of warning about the disaster we're still dealing with. And thanks, by the way, for coming. In high-energy physics, it's made it possible to analyze the data of 40 million proton collisions per second in looking for evidence of the once elusive Higgs boson particle. And in biology, it's enabled researchers to sequence at least one version of the more than 3 billion nucleotides in the human genome, and researchers are now conducting individualized gene research building off this work. In education, the moment for big data is arriving. It wasn't very long ago at all that getting large-scale data in education was difficult. The data was dispersed. Different teachers would each have a grade book, and all that would filter out of the classroom was final grades and disciplinary referrals. The data was inaccessible. It was usually on paper, and it just wasn't very easy to get at. And a lot of the most valuable information was never recorded at all. This led to researchers who wanted to work with big data in education needing to go to heroic efforts to be able to obtain their data. Alex Bowers, a professor here at Teachers College, told me a story about his work. I'd like to share it with you. In Alex's words, for my dissertation, I wanted to collect all of the data for all of the assessments, tests and grades and discipline reports and attendance and so on, for all the students in entire cohorts from a school district for all grade levels, K through 12. To get the data, the schools had it as the student's permanent record, stored in the vault of the high school, next to the boiler, ignored and unused. The districts would set Alex up in the nurse's office with his laptop, and he'd have to trudge up and down the stairs into the basement to pull up 3 to 5 files at a time, and then he'd have to hand enter the data into SPSS. And eventually, he was able to do 10 a day. It's not as hard now. That's pretty hard. That's pretty hardcore. I'm impressed. More and more data is being collected with the idea that maybe it'll be useful eventually. And many large school districts have data officers whose job is to collect the data and steward it, and analytics teams who analyze the data to provide actionable information about what programs are successful for students in the district and other things. But there's even more data than the kind of data that Alex analyzed. Increasingly, there's a new source of data that provides huge quantities of very fine-grained data on student learning that can be used for a wide variety of things. And that's data from educational software. As more learning takes place within educational software and online learning environments of various types, it becomes easier and easier to gather rich data on individual students' learning and engagement within specific subjects. Take, for example, on the top left, the inquiry ITS. Students might use a scientific simulation like this to learn science content and inquiry skills. Or they might learn science content and inquiry skills in a multi-user virtual environment like EcoMove in the top center. They might learn math skills in an action game like Zombie Division on the bottom left. In Zombie Division, the students got a set of weapons that each have a number on them, like a 2 for a sword and a 5 for a gauntlet, and they run around a dungeon, and if they see a skeleton who's got a number on its chest that they can divide with the 2, then they can kill the skeleton with the 2. Or they might learn math. That's a very kind of action game type environment. Some other kids might learn math in a conceptual story-based environment like Reasoning Minds in the bottom middle. Or they might learn it by doing math problems in a workbook-like environment like Assessments on the right. All these environments, all the ones I'm talking about here, generate really rich data streams that have been used in the EDM analyses. And this kind of software is becoming more widespread every day. Systems like the cognitive tutor or like Assessments or Reasoning Mind are being used by tens or even hundreds of thousands of kids each year, 1 or 2 days a week. So what these environments give us is these rich logs. For example, as a student uses one of them, the student will make hundreds of meaningful actions each hour, pausing and thinking before making an incorrect response, asking for help, rapidly changing settings on a simulation, or running away from a skeleton. When the data is logged, these behaviors provide us with incredibly rich detail about learning and engagement that we can analyze. Excuse me. While most of this data is still locked within specific companies or research labs, an increasing amount is becoming openly available for research. For example, today, the Pittsburgh Science and Learning Center DataShop, now led by Ken Kadinger and John Stamper, hosts data from hundreds of thousands of student hours of learning that any researcher in the world can download and study. And researchers are using it. For example, it's enabled graduate students from Brazil to Israel to Nigeria to all over Europe to Vietnam, the Philippines, Pittsburgh, Massachusetts to find data that's relevant for their research questions. Additionally, data is becoming increasingly available from attitude and career surveys. These kind of instruments have been used for decades, but the data used to be collected within a specific school or company, and it was hard to link up even when the same student took the same survey in different years. As the surveys and their data go online, obtaining and using this data becomes easier. And there's data on long-term outcomes. The National Student Clearinghouse and other places have that data. Linking data for the same student across multiple years is still a challenge for a lot of institutional reasons, but the data's there. Increasingly, the data doesn't have to be collected, it just has to be connected. Connecting any two types of data enables us to answer more interesting questions than we can answer with just one. For example, if we have attitude survey data and outcome data, we can ask the question, what attitudes are associated with positive outcomes? Or if we have educational software data and outcome data, we can ask the question, what student behaviors in the learning software are associated with positive outcomes? But as we get more and more types of data, the questions we can ask become cooler and cooler. For example, with these three types of data, we can investigate if students with low interest in mathematics careers are more likely to become disengaged when the material becomes difficult, lowering their probability of learning the material, and in turn their outcomes. So we're getting data, and we're getting more and more of it. As the data becomes increasingly available in large quantities, we need methods for sifting through that data automatically to learn what we need to know, an area that some folks call educational data mining and some folks call learning analytics. To quote the EDM Society's definition, educational data mining is an emerging discipline concerned with developing methods for exploring the unique kinds of data that come from educational settings and using those methods to better understand students and the settings which they learn in. EDM methods have some similarities with traditional data mining methods, but as with other areas of scientific and practice where data mining methods become common, bioinformatics, medical informatics, business analytics, data analysis methods in physics, and so on, the unique features of the domain of education lead to the development of unique methods and lead to some methods being very effective that weren't particularly used in other areas, and other methods that are incredibly popular in other areas not being so useful. There are a lot of ways to analyze educational data. What really differentiates EDM from exploratory data analysis, or even just statistics, is the use of methods that discover patterns in the data automatically. There are a lot of types of EDM methods. My colleague Kalina Yosef, editor of the Journal of Educational Data Mining, and I came up with a taxonomy about 3 years ago. I'll give just a few examples here. One key type of EDM method is prediction methods, which predict a future event from current and past events. For example, predicting whether a student will pass a course from their participation in course news groups over the course of the semester. Prediction methods can also be used to infer an unobservable construct from more observable constructs, like inferring which students are disengaged from their actions in the software. I'll give a couple examples of that one in a minute. Now, it's worth noting that you could build a prediction model by hand. You could look at data, and you could just try lots and lots of models in a stats package. It would take a while. The real power of EDM is the potential to automatically try a lot of different possible combinations of variables and many different ways of combining those variables. Approaches that assume linear relationships, approaches that search for nonlinear relationships, approaches that look for local similarities between groups of students. For example, we think these students all are similar in one fashion and these students are similar in a different fashion. And approaches that assume discontinuities in the data like the one you see here. You say, why is a discontinuity in the data? We would expect to see discontinuities when you note that many educational interventions are either or. A kid gets chosen for an intervention based on whether they're above or below some cutoff. And because of this, a kid's past experience of interventions can show up in the data, producing discontinuities. And you need a lot of data to be able to search for relationships like this. And of course, having a lot of data also helps us to be able to hold out part of the data so we can make sure that the patterns we find aren't just noise, that they work as well on totally new data as the data we found them in. Eventually, we should validate a model with new data from the same students. We should validate a model with data from different students, maybe build a model on 3,000 students and then test it on 1,000 more. We should take data from different populations. We've recently done work with transferring models between urban, rural, and suburban kids, and data from different curricular materials. That way we know that the patterns we find are general. One particularly important type of prediction is assessment of student knowledge. People have been studying how to assess student knowledge from tests for decades. It's a harder problem to assess student knowledge while the student's learning because it's a moving target. But we've made good progress on that one, with models like Bayesian knowledge tracing that have proven to be successful across a lot of different learning systems. It's even harder to assess student knowledge in ill-defined domains like science inquiry, but there's been some really nice recent work on that. Another type of EDM method is structure discovery, where automated methods are used to discover hidden structure in the data. For example, clustering methods can be used with survey data to discover which combinations of attitudes are common in a group of students. So maybe students who frequently have performance goals also are likely to have low self-efficacy. And domain structure discovery methods can be used to figure out why some math problems are harder than others, by discovering what mathematical skills underlie each problem in a curriculum. A third type of EDM method, don't worry, I'm not going to go through 27 different categories here. A third type of EDM method is relationship mining. I just want to give an idea of some of the general categories. Relationships mining is used to find the relationships between a range of variables. And there are a lot of types of relationships that can be found. For example, correlation mining finds out what variables vary together. Researchers often take survey data on student motivations and attributes, and they correlate it with data from prediction models of student behaviors to learn what characterizes the students who engage in those behaviors. And there's also sequential pattern mining, which finds if-then rules that occur over time. Like, if a student's bored, they're more likely to go off task in the next 60 seconds. So these are some of the methods. I'd like to say a few words about what they can be used for. EDM and learning analytics research is mostly used in two ways. First, for basic research, where EDM methods can support answering new research questions and obtaining better answers to existing questions. And second, improvements in educational practice, where EDM methods can tell us things about our students and our instruction methods, leading to more effective, more engaging, and all-around better learning. One recent use of EDM is in supporting formative assessment. EDM-enabled formative assessment software, like Assessments, developed by Neil and Christina Heffernan, and now used by 40,000 kids a year, mostly in Massachusetts and Maine, uses algorithms developed with data mining to infer what students know while they're doing homework math problems. This provides useful formative information for teachers. The software can even predict what a student's eventual standardized exam score will be and what items they're likely to do badly on. As an extra bonus, the software gives each kid help and feedback targeted to what the student knows. So it assists the student while it assesses them. And this can give all of the benefits, or at least many of the benefits, of traditional formative assessment without needing to stop instruction for a half hour to give a test. The kid's doing their homework just like they'd be doing. Instead of doing it on paper, they're doing it on the computer, and the teacher's getting formative assessment data. And just as that's going on, the kid's getting help. Beyond that, EDM methods have been used to assess a number of other constructs, including student disengaged behaviors. And one example of that is off-task behavior, where a student completely disengages from the learning environment and the task to engage in an unrelated behavior. And that can include talking to another student about One Direction. I was just out at some schools a couple weeks ago, and boy, that was all the 12-year-olds could talk about. Or reading a magazine about One Direction. Or surfing the web to read blog posts on One Direction. Or playing an online One Direction video games. Believe it or not, there actually is an online video game for One Direction where you it's like you're Pac-Man and you're going around the maze trying to catch them. Or a student might be off task sleeping and dreaming about One Direction. Another disengaged behavior we studied recently is when students make careless errors. Arnon Hershkovitz and Sweet San Pedro in the audience have been doing some great work on that. Which is making errors despite knowing the relevant skills or concepts. Another one is WTF behavior. It stands for without thinking fastidiously. In WTF behavior, which is common in a lot of learning environments, the student's actively participating in the learning task, but in a fashion that's not really targeted towards successfully completing the task. If you see here, this student's supposed to be plotting points on a graph, and they've instead plotted a smiley face. Another such behavior, and one we've particularly studied, is gaming the system, which is attempting to get correct answers and advance in a curriculum by taking advantage of the software's helper feedback rather than by actively thinking through the material. And this can include behaviors like systematic guessing or help of use. I'd like to show you an example of this. This example is from cognitive tutor software by Carnegie Learning. Software is used in 6% of US high schools. By the way, I want to point out, I'm not trying to bash on cognitive tutors here. We've observed this behavior in a lot of different learning environments. It's been documented in over 40. The example I'm going to show you was identified by an automated detector that we developed using educational data mining methods. So here we see that the student is going to be drawing a graph. The student's already labeled the axes with variables, and in fact, they've also chosen the minimum, maximum, and values of the axes and the scales of the axes in another interface. So all they have to do now is label the values along the axes using a min, max, and scale they've already picked, and plot points, and then interpret the graph. Excuse me. So the first thing a student does is put a 0 as the first value of the x-axis. This is a good value for a lot of graphs. It turns out not to be what the student picked, and it's not really reasonable for height as a variable. So it turns red because it's wrong. They try 0 on the y-axis, which is also wrong. They try 1 on the y-axis. They clear that out. They try 4 on the x-axis. And now they decide, you know, I should get some help. There's this little arrow in the top left corner, if you can see it, where the student can ask for help. And it gives multi-step hints that explain the process of reasoning through the answer, and then eventually give you a bottom-out hint so you don't flounder. And so the student clicks Run Hint and spends 4.8 seconds reading 2 levels of help and typing in the next answer. Now I put read in quotes because that involves reading at 1,000 words per minute, which is faster than adult expert speed readers. But in fact, it says, you've already chosen the first label in the scaling tool, 45. Label the leftmost blank of the x-axis with 45. And lo and behold, the student does so, and it's right. It turns black because it's right. Then the student tries 45 on the y-axis. Unfortunately, that's not right. The student then asks for help. They spend 5.6 seconds reading 3 levels of help and typing in the next answer. And the hints say, actually, you know what? Do the x-axis before you get to the y-axis. Just complete the x-axis first. The second value of the x-axis should be the first value, 45, plus the scale you already picked in the scaling tool, which is 3. 45 plus 3 is 48. So label the second blank of the x-axis from the left with 48. But instead, the student puts on the y-axis, where it's wrong. The student clicks for help again, rereads the same help in 6.5 seconds, and types in the next answer, 48 in the same place. It's still wrong. They reread the same help for the 3rd time, and finally put 48 in the right place. Now, who here thinks this student learned a lot from using the tutor? Raise your hands. Well, in fact, this student got 0% on the unit pretest, which means they've got a lot of room to learn. And they completed 5 problems in the tutor, so they successfully created and interpreted 5 scatter plots of data with this tutor, and then they got 0% on the post-test. So they successfully created and interpreted 5 scatter plots of data, apparently without learning anything about how to create and interpret scatter plots. So this behavior is a problem. It turns out that students who engage in it typically start behind the rest of the class and fall further behind by the post-test. And that's replicated across a bunch of learning environments. Correlation's about 0.3, which doesn't sound like it's huge, but it's actually pretty big for for one thing the student does, maybe 3% of their time accounting for 10% of the variance. We can detect it using educational data mining methods. Our approach is that we collect field observations of student behavior as they use the educational software in authentic contexts of learning, collecting the field notes on an Android app, and then combining and synchronizing those field notes with log files of what the student was doing in the software. So we take the field notes, and the software notes the exact time, while the software the student is using notes the exact time, and we can link them up at the second level. Then we use data mining to develop detectors of student behavior in the log files, finding the features of the student log data that occurred exactly the same time as the observer noticed the student was gaming. Once these detectors have been developed and validated, they can be used in real time for interventions and to conduct analysis on additional log files that are collected. How good are these? Well, hopefully they're decent because I've been working on models of gaming systems since 2003. And in fact, after 9 years of work, I can say that we can distinguish a gaming student from a non-gaming student 96% of the time, which is pretty good. They achieve a correlation to the frequency of gaming behavior of 0.9 and a correlation to off-task behavior of 0.62. They can determine exactly when these behaviors occurred about 40% better than chance. So in other words, they're better at catching exactly what students do. They're better at catching exactly which students game or go off task than catching the exact moment. And that's in part because sometimes the examples aren't exactly clear. And they can predict student behavior accurately for new students, new tutor lessons, so new mathematical topics, new populations, urban, suburban, and rural kids, and even new countries. We found some evidence that these kind of models transfer between students in the US and Philippines, and we're working on data from Mexico and Costa Rica. It's kind of an off topic for the moment to talk about, but I actually don't think the models are going to work quite as well in Mexico and Costa Rica, based on other evidence we've seen that students tend to use the software in different fashions in those countries. You might be saying, how can you tell? How can you tell what students off task from what they're doing in the software? Maybe the student's just talking to the teacher. They both look like pauses, right? Well, in fact, we can't tell from the pause itself. What we can tell from is what happens immediately before and after the pause. A student who's off task tends to be working kind of quickly, not really getting stuff right or wrong more than other kids, kind of working in an average fashion, and then they have a long pause, or maybe 2 long pauses, and then they go back to working kind of quickly. A student who's struggling but looks completely different. They make a lot of errors, they work slowly, then they have a long pause. Usually after the long pause, they get it right, and then they go back to working slowly. So that's why we can tell these things apart. Not by what's happening during the pause, which is completely outside the software, but by what surrounds it. Beyond this, some recent work from our lab and other labs has been able to infer student emotion. Take the student on the left. Is he bored? Is he deeply engaged in a positive fashion? Frustrated, right? Take the student on the right. Is she bored? Is she frustrated? Or is she deeply engaged? People can tell the difference between these kind of emotions, and people can do so about 60% better than chance. The latest EDM models that try to infer this just from log files are about 25% better than chance. So we're a little over the third of the way there. It's not perfect, but it's a start. And it's worth mentioning that it was only 16% better than chance a year ago. The vigorous competition between different groups is bringing these numbers up as we figure out how to do this better and as we develop new methods and then borrow each other's new methods. So this is moving really fast as a research area. Now, these kinds of models can be used by teachers to find out what students are more and less engaged so that the teacher can focus on re-energizing these students. It's not always obvious which students are disengaged, particularly in a large class. A teacher can tell which students are being disruptive, but not all off-task students are disruptive. A lot of them are very quiet. They're quietly off-task. And students who are gaming the system actively try to hide it from their teachers. Similarly, finding out which students are frustrated and when, and even more importantly, why, what material is frustrating them, can enable a teacher to provide a student with extra support on exactly what's frustrating them. So it can be a really useful tool. So these days we can assess a lot of things. But this kind of work is just the tip of the iceberg in comparison to where we're going, what we'll be able to do in the near future. Because assessing where a student is right now, what they know, what they're doing, what they're feeling, well, that's useful. But it's not enough. We also need to know where the student's going. We need to be able to answer questions like, is this student going to pass or fail the course? Is the student going to be prepared for the next course? Is the student going to be prepared to learn new skills when he or she enters the workforce and succeed in his or her career? And are motivational factors going to get in the way of the student's success? Is a student who's perfectly prepared at a cognitive level going to think, career X isn't for me, or I can't succeed in career X, and therefore make that perception a reality? To put it another way, when we talk about the pipeline of students becoming ready for 21st century careers, where is the current student most likely to drop out of the pipeline? EDM methods are proving to be useful for this. For example, recent EDM work has been able to predict which students are prepared for future learning, more likely to do well when they get to the next topic in class. You can see here that the red and blue student are doing about equally well on the first topic, but then they diverge on the second topic. And we can now predict that this divergence is going to occur early within topic 1 for some educational software. The model that predicts this actually builds off of models of student behavior in the software, including whether students game the system and how they use the software's help features. It turns out that the students who are likely to be prepared for future learning are the ones who seek help when they need it. If the system tells them they have a misconception, they pause and read it and think about it. They don't game the system, and they tend to learn to work quickly when they know the material. These kind of methods can also predict which students are more likely to fail the class. In this case, both the red and blue students from before end up passing the class. The green student's behind from the beginning and never catches up. And researchers have developed models that are able to predict failure in online classes from very early in the semester. One colleague told me that after 2 online class sessions with online discussion, they can actually predict which students are most likely to fail. And EDM methods can even predict which students are more likely to drop out of school or drop out of university. The Purdue Signals project has been successful at identifying this early in a student's university sequence and passing information about that to TAs and course instructors. So with educational data mining, we can predict the future. But is it enough just to predict the future? What if we predict the future and then we don't do anything about it? The reason to predict the future is so we can change the future. For example, if a detector can infer student progress and emotions during homework, it can give teachers reports or send teachers emails on what material was hardest for the class and which students got frustrated and when. This helps teachers know how to adapt class the next day and which students need extra support. The assessment system already gives teachers and parents reports about what material was difficult for each student. Kids love that one. And we're building an engagement and an emotion detection capability. This information can also be useful to principals and other high-level school and district administrators. For example, it'll be possible to obtain formative data as to engagement in different classes in schools, and a principal can find out in mid-semester where greater support might be useful. At a more micro level, we'll be able to know what student decisions impact learning, so we can know what the critical moments are, so that we can know what directions we should nudge students in to help promote their learning, their engagement, and their growth. Look at the graph on the left. Take, for example, a student has a misconception and who gets some feedback on that misconception from the learning software. They then have a choice of whether to self-explain that feedback or just to kind of move on. And it turns out there's a lot of research that if they don't self-explain it, they don't learn as much as the students who do self-explain it. So we have a student who gets the feedback, doesn't self-explain, they're in danger of not learning. But if an EDM-based model can catch that they don't self-explain, then we can intervene so that they can learn better. And sometimes it should be the software nudging the student. Other times it should be a teacher, or a parent, or even a friend. We don't really know as a field when different types of support and different supporters are most effective for this kind of thing. There's still a lot to learn. We're going to need to leverage everyone we can, working to include and empower everybody who can help the students learn. I'd like to give a quick example of how we can use detectors to do this. It comes from my group's research on gaming the system in middle school math. As I mentioned a few minutes ago, students who game try to get the answer without learning the material by systematically clicking through hints or guessing to get the answer, and then moving on without thinking about the answer. Across several studies, we've seen that students who do this start out behind the rest of the class and fall further behind by post-test. So we developed an automated detector that could identify when a student was gaming, and we built it into a cartoon character, Scooter the Tutor. And Scooter responded to gaming in 2 ways. First, emotional expressions. If the student never games, Scooter dances around and looks happy. But if the student appears to be gaming, Scooter looks increasingly upset and gets redder and redder. And occasionally I get the question, did students get upset by Scooter getting mad at them? The answer is no, not really. In fact, the boys, the 12-year-old boys, thought nothing was more fun than to sit down and have a happy Scooter and see who could get Scooter mad faster. Scooter also gave supplementary exercises that covered the material the student had bypassed through gaming, giving students another way to learn the material they'd missed. The result of implementing Scooter in a classroom was that about half as many students gamed the system. 17% of students gamed when Scooter was present, as compared to about 33% in the same tutor lesson without Scooter. And better yet, students who got Scooter's intervention actually caught up to the rest of the class. The pink line is the students who didn't get exercises from Scooter because they didn't game. And the blue line is the students who gamed and got exercises from Scooter. And you can see that the pink line starts out way above the blue line. Students who gamed started out way behind to begin with, but by post-test, they actually caught up to the rest of the class. By contrast, we can look at the control condition, where, once again, the students who gamed the system less, according to the detector, the pink line, started out well above the students who gamed the system more and would have received Scooter's intervention in the other condition, the blue line, but the blue line fell further behind by post-test. So if you compare those two blue lines from experimental to control, you can see what a difference an intervention based on an EDM detector can produce. This is just one example of how predicting the future can change the future. Predict the future. We detect that a specific student's gaming a system, and they'll learn less than other students. Change the future. We intervene right then to give them a different way to learn the material, and they catch up to the rest of the class. With educational data mining, we'll be able to go beyond assessing where a student is now to predicting the future. We can determine where a student's disengaged, where the student's struggling. And then we can use that information to change the future, helping students to engage and to develop deep and robust learning. Models developed through educational data mining can help to support students better and help teachers and school administrators to support students better. With EDM, we can cut off the arrows that lead the student away from career success, or at least we can weaken them. We can catch when a student's at risk of failing a class, and then provide them with better and more targeted learning support, and equip the teachers with useful information to help these students catch up. We can catch when a student's learning is shallow, and they'll succeed now, but they won't be prepared to learn later or to succeed later. And we can help them learn more deeply so that they don't just succeed in the current course, but learn what's necessary to prepare them for future learning. Eventually, we can infer what trajectories through a course sequence and what learning experiences indicate that a student is or isn't prepared for their future career. And we can alter the curriculum to improve the support for those students. And finally, we can figure out when motivational and attitudinal factors are likely to hold a student back. And we can provide that information to teachers and guidance counselors and as appropriate parents. And not to mention, we can use that information to help select enrichment experiences for the student, to engage and excite them about their future opportunities. There's a lot of after-school programs out there that are out there to excite kids about science. The process of getting kids into those programs is kind of an inexact art. If we can figure out exactly which kids are ready to do well in those careers, but don't think those careers are for them, then we can do something about it. We've actually got an ongoing NSF project to try to do exactly that. And there we are. At each stage of a student's progression to eventual success, there may be something that EDM and EDM-based interventions can do to help. There's going to be a lot of work necessary to get there. We need to get the data, we need to use that data effectively, and then we need to do thoughtful design in partnership with teachers and other relevant folks to develop appropriate and effective interventions that leverage those detectors. There's a lot to do for EDM to be of full use to the education, research, and practice communities, and for EDM to achieve its potential of enabling new and more effective ways of supporting learners, teachers, school administrators, and parents. EDM can help us predict the future, but it's up to everybody here to help change it. So I'd like to conclude by just saying that the work I've discussed today is dependent on partnerships with colleagues and students in a wide variety of areas and will continue to do so. I'd like to thank all of them, in particular Arnon Hershkovitz, Sweet San Pedro, and Adriana Di Carvalho, who are here today, and the various funders, including NSF, Department of Education, Pittsburgh Science and Learning Center, and the Bill and Melinda Gates Foundation for their generous support for this kind of research. Also, clearly, Teachers College, which is becoming an institution with a lot of investment and a lot of value for these kind of ideas. I'd like to also thank you all for coming and thank you for your time and say that I look forward to your questions. Thanks again.